Hi, and welcome to the Rohde & Schwarz series on pulse measurements with the Vector Network Analyzer. My name is Yasin Mikhailov, a product manager for network analyzers, and I have our guest today, Jamie Lunn.
Hello.
So hi, Jamie. In the first video, we discussed fundamentals of pulse measurements. So in what case we would use pulse measurements, what's an RF pulse, and what are the three main categories for pulse measurements. And today, let's talk a little bit more about average pulse measurements. Why and where would we use average pulse measurements?
Thank you, Yasin. So, as we said in the first video, average pulse measurements are traditionally the way that we address these kind of measurements with a network analyzer. To understand a bit more about their pros and cons, we need to understand a bit about some of the fundamental limitations with how the line spectra looks in the frequency domain. So if we look at the repeating pulse waveform here, then as we saw in the first video, each of the RF pulses contains a snapshot of what the CW signal actually looks like. And over time, then this gives us an average pulse power value. If we look at this in the frequency domain, then as we saw before, we get this classic sin x over x envelope or response of the magnitude of these line spectra, where the central one is the key element because that effectively gives us what's referred to as the DC value. It's the frequency of the carrier or the carrier frequency. And so if we can use a technique which somehow filters out just that central component, ignores the rest of the line spectra, then from the network analyzer's point of view, we effectively are just looking at a CW signal. But it does have a limitation in that effectively the dynamic range, the power that we have going into the receiver is limited by the duty cycle.
So in this average technique, we're just focusing on the centerpiece, on the carrier frequency.
Correct. Yep.
And this doesn't put any specific stress on the test equipment.
We don't have to trigger the measurement, but what we do have to do is be careful about the measurement bandwidth that we choose for the setup, because fundamentally the measurement bandwidth, the receiver of the network analyzer, is what's going to perform the job of filtering out the rest of this line spectra. Now in the past that can be quite challenging to figure out which one is the optimum one to use. Inside of our network analyzer, or the ZNA network analyzer, we actually have a mode which makes this task much simpler. And it's effectively using a measurement bandwidth with a high selectivity receiver. And as we can see here, this effectively gives us a filter bandwidth profile without all of these ringing elements. So a much sharper roll-off of the spectrum outside of our filter bandwidth.
So what was the challenge in the past? I think it has to do something with the filter, with the traditional filter and the side lobes?
Yes. So the key thing was to make sure that we optimally suppress the adjacent side lobes in the frequency spectrum. So if we look here, here's an example where we can see in blue, this is our pulse spectrum. So we can see each of the line spectra. The central component is the one that we want because this contains the information about the carrier frequency. And overlaid here, we can see what the filter shape of our network analyzer filter looks like. And in this particular example, we've got optimum filtering here of those adjacent side lobes.
I see. That's very interesting, fantastic that we don't have to have any worries about the test equipment and that we have made our life easier with these high selectivity filters. But you did mention something that kind of caught my attention. What about the pulse desensitization, you called it? Could you tell me more about this?
Sure. Yeah, this comes back to the fact that from the network analyzer's perspective, it's really just seeing the average power. So if we take an example here where we have a duty cycle, in this particular case of 10%, so a pulse width of 1 microsecond and a pulse period of 10 microseconds, then this gives us a reduction in the average power, which is effectively 20 log of the duty cycle. And we can see that here in the measurement of the absolute power being received into the network analyzer, where we were expecting 0 dBm, and the magnitude of this first null has dropped by 20 dBs. So it depends on the duty cycles, but as we go higher in power, we're generally forced to use much wider or greater duty cycles to reduce the average power so that we don't get problems with thermal effects and potentially the device being destroyed. But the trade-off with that is we get much less sensitivity or reduction in dynamic range.
That's an interesting point that you bring. So the higher the power, the greater the duty cycle, the more desensitization we have. So could you show me an example? How does this look actually? What's the challenge there?
Yeah, so if we think about a basic bandpass filter, I've got a picture here which shows a filter response where we've overlaid various memory traces of the measurement at different duty cycles. So the first one here is, if we look at 100% duty cycle, that's of course a continuous CW signal. So there's no reduction in power due to pulse desensitization. And in this example, we have a noise floor of about minus 135 dB. If we now turn on our pulse stimulus and look at the same measurement with a 10% duty cycle, you can see nothing's changed at the top part of the pulse. So we're making measurements here very accurately, but what we have done is moved our noise floor up because we've lost signal to noise. So we're now at minus 115, so there's 20 dBs of desensitization. If we move to a 1% duty cycle, now we lose another 20 dBs, so we're at minus 95 dB, and so on, at 0.1% at minus 75 dBs. So this is where the problem becomes much more apparent as we're working towards larger duty cycles, where we're really getting to the issue where we're starting to run out of dynamic range.
So essentially, even if we're measuring a simple filter and we're trying to focus on the band reject, let's take an example where this filter is part of a front-end module. With average pulse measurements, we face significant challenges due to its desensitization. So Jamie, could you show me on the network analyzer, how do we perform average pulse measurements? How do we do this actually?
Sure, let's have a look. So what we've got here is a measurement where we are sweeping from 8 gigahertz to 12 gigahertz. To get a better indication of what's happening to the pulse power, I'm going to change our trace here to look at the absolute power being received onto our reference receiver here at port 1. So that's the A1 wave. And if I'll just pop a marker on there, we can see that's measuring minus 10 dBm, which is what our stimulus power is. If we go into the pulse menu, I'll quickly pop into the schematics dialog, and we can see a schematic representation of the way the pulse generators are fed into the pulse modulators. So we saw that in the last presentation. I'll enable pulse generator, but I won't do anything else here. We've got a 10% duty cycle, so our pulse width is 10 microseconds, pulse period is 100. Click OK. And now we can see that something strange happened here. Our power's dropped down, but it isn't stable. It's kind of on and off through the frequency. If we come back into this menu, and what I'm going to do now is just reduce our measurement bandwidth to say 1 kilohertz. And you can see that the dialog has already given us an indication now that it's using a narrowband technique. And we should expect the power to be desensitized by approximately 20 dBs. Let's click OK and see what that's done now. And clearly here, that's done exactly what we expected. Our power's dropped to minus 30 dBm. And if I just toggle the pulse measurement on and off, we can see that 20 dB difference. And if we, for instance, go in and just change our measurement bandwidth, as we increase it, we can see we're right on the edge now. So we're no longer filtering out those adjacent frequency spectrum when we looked at the frequency domain. And over on the right-hand side, we have our high selectivity filter. If I just click that, then that brings us back to where we were here at minus 30.
Very interesting. So this is as simple as that. Just click from normal to high selectivity filter, and there you go. In average pulse measurements, we have a clean signal. Is this an option, or is this standard with
No,
the
this
instrument?
is a standard feature with the ZNA network analyzer.
Fantastic. So what happens, I mean, you increase the IF bandwidth now. What happens if you decrease the IF bandwidth? Should we expect any effects on the measurement?
No, that's where it's a bit strange, because we are normally used to thinking about reducing measurement bandwidths to gain better sensitivity because the noise floor improves. But in this case here, effectively, the measurement is the same regardless of what measurement bandwidth we're looking at, because we're still looking at that same magnitude of power in that central frequency component. So there's actually no benefit in using a much lower measurement bandwidth.
So actually disadvantage, because we're slowing down the measurement, correct?
Correct, yes.
Great. So thank you, Jamie. That's fantastic.
Thank you, Yasin.
So in this short video on average pulse measurements, you saw the advantages and disadvantages of average pulse measurements and how to perform those with the VNA. So the advantage was that there was no special needs or requirements on the test equipment. The disadvantage, however, was the pulse desensitization, where you lose dynamic range. And in the next short video, we'll show you how to overcome this disadvantage with point-in-pulse measurements. Hope to see you soon.